today is Matthias Zach from Hannover University, and he will talk about topology of isolated determinantal singularities.
Thank you very much. First question, do I need the microphone? With microphone? Okay. You tell me when I better should use it. So, thank you very much for inviting me here. It's a great pleasure to be here in Mexico and also meet all these people. Many people that I don't get to see that often and I like to work with, and many other people. Although I have to say that now that I'm here and I see who made it here, you probably know already the contents of this talk. But I will try to sell it to you in an appealing way for generic geometers. And I would also like to use this occasion to make a little commercial for a workshop on determinantal singularities that my former supervisor, Anne Frübes-Krüger, and me will host in my home university, Hannover, in the beginning of March next year. And therefore I would like to get you interested in this field of study. To introduce determinantal singularities, I would like to show you how this naturally generalizes the cases you know. And the cases you know, or I assume you should know, is the case of an isolated complete intersection singularity. And one way to give a definition of an ISIS is to consider it to be given by means of a map germ small f from Cn to Cp, and then you have certain conditions, wrong direction, such as the space where the zero fiber of this map, x0, should have expected codimension. You take the preimage of 0, 0 has codimension p in Cp, and then this should be the codimension of the fiber of 0. And then you want the singularity to be isolated, which then means you can show this, that this is equivalent to f, the map being regular in a punctured neighborhood of the origin in Cn. And you should note that this is a condition which is not only living on the singularity x0, the geometric space, but really in a neighborhood of the ambient space. If you go from this to determinantal singularities, this is a definition I would like to give that was originally coined by Wolfgang Ebeling and Sabir Gossein-Zadeh in around 2010, I think. An essentially isolated determinantal singularity is given by a very similar setup. We consider a holomorphic map germ. This time the target space is the space of matrices, M by N matrices. And because every matrix is either called A, B, or C, we call our map germ A instead of small f. And then in this space you have the generic determinantal variety, the matrices of rank strictly bounded by T. And there you also already see the three numbers. Every essentially isolated determinantal singularity has a type, M and T, and it's exactly these three numbers you see appearing here. M by N matrices and rank less than T. And then there are certain conditions very parallel to the ISIS case, which is we consider now not the preimage of 0, but the preimage of this generic determinantal variety you see here. This is the geometric space, the singularity as a geometric object. And we have the same condition to have expected codimension. The codimension of the generic determinantal variety is easily computed to be this, and this should be the codimension of the singularity as a geometric object. And then the isolatedness is different from the geometric intuition probably, but it's also a property that should be fulfilled on a punctured neighborhood of the origin in the whole ambient space of the singularity. And the condition is that this map A is transverse to the canonical Whitney stratification of this space of matrices. The Whitney stratification is given by this M and S for increasing or decreasing S. You have a stratification by rank of matrices. Well, this is an essentially isolated determinantal singularity. And now the big question is, why determinantal singularities? Well, I already tried to show you it is very parallel to the ISIS case, and you can consider deformations of determinantal singularities. And there's a class of particularly well-behaved deformations, which is the determinantal deformations. If you deform an ISIS, you just perturb the defining equations of your ISIS. And if you deform a determinantal singularity, you just perturb the entries of the matrix. You perturb the map A going to the space of matrices. And when you do this, then the contact equivalence for ISIS naturally generalizes to the so-called G equivalence. This is very similar to what we saw 2 talks ago. G equivalence is maybe not the same G equivalence, it's not the same that appeared there. The term is coined by, I think, my supervisor, Anne Frübes-Krüger, who named this group G. Okay, when are two maps A and A prime defining the same singularity up to G equivalence? Well, if there exists a diffeomorphism in the source, phi, and two matrices P and Q, both with holomorphic entries, such that if I compose A with this diffeomorphism, it's the same as multiplying from the left and from the right with P and Q. Next step. This is results that Miriam da Silva Pereira proved in her thesis, I think also 2010, or was it later? 2010. Yes, at USP in San Carlos. She may not have used the name EIDS, but different. She developed a different, the same notion but with a different name, probably. The following are equivalent. We have, if a matrix defines an EIDS, then this determinantal singularity is finitely determined in the G equivalence setup, which allows us to reduce to algebraic settings, which is particularly nice if we want to do explicit computations, because we always have finite input data, which is better than infinite input data. And then there exists a semi-universal unfolding of A, of this determinantal singularity, and the base space of this semi-universal unfolding is smooth germ, some C to the tau. So this is unobstructed deformations. And another feature that the algebraists among us might be very fond of is that we also can write down a free resolution of this OX0 as a CX module. And this is another way in which determinantal singularities generalize the ISIS case. If you have an ISIS and you want to write down a free resolution of OX, then you can just take the Cauchy complex and substitute the generator with the generators of your ideal. This is from ISIS being complete intersection. And something similar holds for determinantal singularities in the following sense. You can take a free resolution from the generic determinantal variety. And here the coordinates y, I want to take the coordinates of the space of m by n matrices as an affine variety. So we have y11 up to ymn entries of the generic matrix. These resolutions have been computed by Lascaux in his thesis, I think, back then. But there are he uses representation theory, and he can only do it in fields of characteristic 0, I think. But since we're working over C, we don't have a problem. And if we take this free resolution, we obtain a free resolution of our determinantal singularity just by substituting the matrix entries for the Yij. And as a consequence, since the generic determinantal varieties are Cohen-Macaulay, and this is a matter of the length of this free resolution, we get that also the determinantal singularities are Cohen-Macaulay. And here I trust that everybody who's interested in the algebraic setup knows for him or herself why Cohen-Macaulayness is a nice property. One nice property is that you can use this to show that determinantal deformations, that means those coming from a perturbation of this map term, induce flat deformations of the space term. All right. The existence of semi-universal unfoldings enables us to write down, to construct a unique determinantal Milnor fiber. And one way you can do this is you start with an EIDS of type MMNT, and you always need to fix the defining matrix, of course. And then you write down some semi-universal unfolding, and I denote this by Fat A. It's now a matrix depending on the affine coordinates x and also the deformation parameters u. It's finitely many. And if we want to construct a Milnor fiber, you usually start by taking a suitable representative, then cutting out by some Milnor ball, and then you deform in a general way. In the semi-universal unfolding, you will have some kind of discriminant where the fibers are still badly behaved, and some open set, the complement of the discriminant, over which you have a generic fiber, the stabilization of your singularity. And the intersection with this Milnor ball, if you perturb small enough with respect to the chosen representatives, this is the determinantal Milnor fiber I would like to consider. And to take this back to the world of maps, I think it's rather intuitive if you keep in mind here you have the Cn and the map A, taking it to the space of matrices, and here you have the generic determinantal variety M, M, and T, and then A takes this Cn, somehow probably folded in here, and now we perturb A generically, and we take some AU for generic U. The generic determinantal variety stays fixed. And now the image should be as generic as possible, which might result in an image like this. And then it's easy to believe that the image of this generic perturbation is transverse to all strata of the Whitney stratification here in the target space. And as a consequence, this determinantal Milnor fiber is smooth if we can move away the image from the next lower dimensional stratum, which is in this picture would be this, mnt minus 1. If we can move the image of A away from it, as should be the case here, then it's transversal intersection of smooth manifolds and everything well behaved. And in numbers, of course, this is the condition, the codimension of this lower dimensional stratum must be strictly bigger than the dimension of the Cn we send over to the other space. And if this is not the case, if the determinantal singularity is not smoothable, then the singularities that we inherit, they appear under transverse maps, which means they have very simple form. There have been several different approaches to compute the Euler characteristic of these determinantal Milnor fibers. And the first one I would like to mention here is due to Jim Damon and Brian Pike, who applied much more general machinery, where I have to admit that up to this day I did not really go through all the details of their article. But they found a way to compute the Euler characteristic of determinantal Milnor fibers, and this was the starting point of my thesis, because what they were able to compute revealed rather unexpected behavior. But let me also give you some other formulas. Here a formula due to Juan José Nuño Ballesteros, Bruna Orefice Okamoto, and Juan Tomasella. And this formula for me is nice because I understand it. And what you see here is the Euler characteristic of the determinantal Milnor fiber. And the cases they consider is only smoothable EIDS. And then here on the other side you see, you see the multiplicity of the singularity, which is an algebraic invariant and can be computed. And what you see here is the so-called polar multiplicities, which if you have a computer algebra system and you know the right equations to put in, for example singular, you can also compute this. So this can serve as a substitute for the very famous formula due to Milnor. Milnor computes the Euler characteristic of a Milnor fiber of a hypersurface just as the length of the Milnor algebra. So you have an algebraic invariant which describes the topological invariant. Algebraic invariant is much more easy to compute, and this is also a way you can access this topological property of determinantal singularities from an algebraic formula. There has also been work on the non-smoothable case, here by Terence Gaffney, Maria Ruas, and Nivaldo Grulja. They have an article on the Euler obstruction of the generic determinantal variety and also the associated determinantal singularities, and they also use polar multiplicities. And the original article from which also the definition of EIDS comes by Wolfgang Ebeling and Sabir Gussein-Sade, and they use indices of one forms, which is a nice differential topology approach, but it doesn't serve well for computations. Okay, the Euler characteristic can be computed, but what about the different Betti numbers? The different Betti numbers of this determinantal Milnor fiber, usually if you only work in the ISIS case or the hypersurface case, you know there's only one non-trivial Betti number, because the Milnor fiber is a bouquet of spheres. And all these spheres have the same dimension. So knowing the Euler characteristic is already sufficient to have these topological invariants. But as said, that Brian Pike and Jim Damon, they saw unexpected behavior, and this unexpected behavior when they observed the Euler characteristic was that, oh my god, there must be two non-zero Betti numbers in certain cases. And my task in my thesis was to find out about these Betti numbers. This is the theorem I came up with together with my supervisor, Anne Frübes-Krüger. And you see these rather awkward assumptions and conditions on the singularities in question. What you have to keep in mind when you see the assumptions and made in the statement of this theorem is that we had a sandbox of singularities. Namely, my supervisor Anne Frübes-Krüger classified all the simple isolated Cohen-Macaulay codimension 2 singularities, also around 2010, together with her former student Alexander Neumann. And they obtained a list of singularities from dimension 0 up to dimension 4. Up to dimension 3, the singularities are smoothable. And this is a very nice list that has now been used all around the world as sandbox to apply theories and test hypotheses. And the simple isolated Cohen-Macaulay codimension 2 singularities, which come up naturally from this classification, they all happen to fulfill all the requirements of this theorem. So this is how these awkward assumptions came about, but the result is rather nice. We have a description of the homology groups of this determinantal Milnor fiber. It's threefold singularities. The third homology group is free of some rank B3, so far so good, as expected. But then we have another contribution in degree 2. And this is special, and this is a contribution which is also generic, because we will see that it always happens independently of which entries we put in the matrix. Moreover, we have a formula to compute this rank up here as the sum of Milnor numbers of the singularities that can be found in the Turiner transform. Now, I did not explain you yet what the Turiner transform is, but it's a rather technical construction that we did, and I will explain to you now. Good. The Turiner transform is basically one huge diagram. You start with a determinantal singularity x0 and a deformation whose generic fiber is the determinantal Milnor fiber. Say stabilization of this map. And then, wrong direction. Then here, the total space of this deformation naturally appears as the preimage of this generic determinantal variety under the associated map defining the deformation. And from the generic determinantal variety you have two natural rational maps to certain Grassmannians. Here I choose one and I take a matrix of rank t, of rank t minus 1, and I map it to its kernel. This is a map to this Grassmannian. And of course, where the rank drops, if the matrix does not have rank t minus 1 but even lower, then this is not well defined. And we can resolve the indeterminacy of this rational map, and we obtain a strict transform I call WMNT, together with a projection to the original determinantal variety, and a natural prolongation of this rational map to the Grassmannian that I will call L. And then the Turiner transform in family for our singularity is defined as the fiber product of these two maps, pi and fat A. We get a projection down to X, and for the singularity itself, of course, we only take the fiber in the family. And then you get also the singular locus of x0, which naturally appears as the preimage of the next lower dimensional stratum here, and some exceptional set. So you can imagine this map to be some blow up, but not in the usual sense, but in this weirdly constructed sense. It replaces the singular locus by something compact. And what is this compact object? It's the exceptional set E0, and it's, in case you have an isolated determinantal singularity, it's just this Grassmannian you plug in. Why do we do it this complicated way? The big advantage is that we have very explicit equations from this. Let me give you this example. This is from the list of simple isolated Cohen-Macaulay codimension 2 singularities in C5. This is the matrix that describes the determinantal singularity, and from this matrix you directly get the equations for the Turner transform. So the Grassmannian that you have on the very right hand side of the former diagram is just a P1. You have the kernel will be one-dimensional in 2 space. This is parameterized by P1, and the Turner transform is then naturally lives in this product space. You take homogeneous coordinates of this P1, S1 and S2, and then you get 3 equations which are just given by this product. And this gives you something in your hands. You don't need to do saturation processes, you don't need to take the closure of the image of a graph of a rational function where you lose control over the equations. You have control over the equations. And if you're lucky, then the Turner transform is a local complete intersection scheme. And this is the case if you don't put in something of too big dimension. You replace the singular locus by this Grassmannian, and if the Grassmannian is too big, then all our theory doesn't work. But if the Grassmannian is small enough, in this case we plug in a P1 into a threefold. This doesn't change the dimension of the threefold. And then the dimension of the Turner transform is equal to the dimension of the original singularity, and we have a local complete intersection. So we jump to the realm of singularities that we already know and where we know how to treat the topology. So let me give you a sketch of the proof of our theorem that I showed you before. What do you start with? Well, an isolated singularity is always conical locally. So it retracts to the singular point. If you replace this singular point by something compact, then everything will contract to this compact set. In this case, you replace it by a P1, it's a 2-sphere. You get a homotopy equivalence of Y0 with this P1, with this exceptional set, and an induced isomorphism of homology groups. And what could this look like? Well, let me try to draw a picture. So this is our Turner transform, or part of our Turner transform, Y0 bar. And we have the exceptional set, which comes in from infinity, goes here. So this is E. And by assumption in the theorem, we only find isolated singularities in the Turner transform. We can choose some Milnor balls around these singularities. So this is B1, for example. And when we proceed, we just observe the local change in topology in the Turner transform. And then we glue to get the global picture. Well, we deform this scheme. It's now a global deformation of a global scheme, not only of one singularity. But on the smooth part, nothing happens if you only consider this as differentiable manifolds. So you will get the same picture. The Milnor ball comes in here, and now you have a local Milnor fiber which could look like this, with some vanishing topology here. And then you only need to glue all this together to get the global picture, which means you look at the long exact sequence from this pair of spaces. Here's my pointer. This pair of spaces, y0 and the part here in the Milnor ball. From this, okay, here we have y delta bar. From this side at y0, you get an isomorphism in degree 2. Here with this relative homology group, which basically replaces the generator of the degree 2 part by a relative cycle. The generator is the fundamental class of this exceptional set. It gets replaced by a relative cycle, and this relative cycle naturally carries over to the other side. And now you jump to y delta, and you again get an isomorphism in degree 2, which geometrically means that this relative cycle, its ends lie in the boundary of the local Milnor fiber, and it's connected enough so that it can close again and form a global cycle for y delta bar. And this is the mysterious degree 2 contribution. And then for the degree 3, you essentially play the same game. You have, no, not the same game. You look at the local Milnor fibers here, what you find inside the green ball, and you show that you have zeros in the long exact sequence of this pair of spaces, so they naturally carry over to generate the third homology group of y delta bar. In this case, this is about these vanishing cycles that come from the isolated singularities in the Turner transform. All right, this is how you end up with this theorem. And what I would like to ask you as people working in generic geometry of maps is whether anybody is familiar with this setup. Here we have the intersection of the image with the generic determinantal variety, and its pre-image here. Okay? And here we have the same, which now might look like this. And this degree 2 contribution to the vanishing homology that you see there, it comes from here, from a cycle in the link of the generic determinantal variety. And it always carries over to the other side by means of AU. It's in the pullback of the cohomology, if you consider the cohomological side. And this is something I would like to understand better, and maybe one of you has an idea from these pictures, and I would be happy if we could discuss this together, whether there's a setup where this appears in other contexts. Okay, to finish my talk, I would like to, where's my point? Here's my pointer. I would like to tell you how I generalized this theorem, because, as I said, these assumptions of the theorem came up naturally, but they are rather awkward. And you want to eliminate some of these conditions. Now I don't want to eliminate the dimension 3, because this is the only dimension in which these phenomena are visible. You could do other matrix sizes, but the matrices can't become too big, because otherwise the Turner transform is not a complete intersection anymore. So let's fix the matrix for now and see what we can do. The most unpleasant condition is that we require isolated singularities in the Turner transform. This happened for the simple singularities, but apart from that, there's no reason why this should happen. So let's erase this condition. And this is the theorem that holds in general, or for non-isolated singularities in the Turner transform. And I allowed the matrices to grow at least in one direction, because then still I have control of the local complete intersection scheme structure. And the same result holds, as you see. In this middle block nothing changes, only that we need a different formula to compute the third Betti number. This is a tautological formula, of course, if you know this. But it's useful in the sense that I can algebraically compute the right-hand side by either of the formulas I showed you before, from the authors I mentioned before. Good. Let me give you a sketch of how to prove this theorem for the rest of my talk. I still have how long? 15 minutes. Yeah. This should be enough. I will draw some more pictures. Sketch of the proof. First, let's try to imagine what a Y0, a Turner transform with non-isolated singularities could look like schematically. Well, you could have a space like this. Here, but with the exceptional set has to appear somewhere. It's again a P1. So here's our exceptional set E, a P1. And let's suppose that we have Whitney umbrella here and here. And then we also have generic, if we take a transversal slice, say like this, then here we have an A1 singularity. So this is what I call Y0 transverse, and this is L was the generic projection to the P1, and it's a generic section, or a generic slice of this projection. And we consider a generic rank 1 perturbation, which is now not a generic perturbation, but a perturbation of this defining matrix by another constant matrix of rank 1. The reason for this is rather technical. It will be that we have an axis of this deformation. By this I mean a fiber at infinity. Let's put infinity down here. Here infinity on P1. And the fiber of infinity is also just an A1 singularity in this case. And the deformation will, by a generic rank 1, the generic rank 1 perturbation will preserve this fiber at infinity. And then we can first look at the other chart, and we know what happens at infinity. Nothing happens for now. We have to stratify this space. Intuitively, one stratum, of course, should be the smooth locus outside the exceptional set. And then we have as a next, as a candidate for the next stratum, of course, the exceptional set, but then there will be some special points here, the Whitney umbrellas, and you also need to take into account certain points where polar curves hit the exceptional set and so on. It's all in my article on the archive. But this stratification exists and is finite. And then we choose Milnor balls as before around the special points. So here B1, here B2, but we also need to take care of the other singular locus and take some tubes around these loci. This is this step, so this is N. I think this marker is giving up. Let's see how far we get. And then we deform with this generic rank 1 perturbation. We pass from y0 to y delta. It's now, I can't switch this blackboard, unfortunately. Y delta, nothing happens on the smooth locus. So we again get this picture. But now some things happen in the Milnor balls. We have B1, B2. What could happen? It could happen that what we have looks like this. And then also this other tubular neighborhood of the remaining singular locus of the non-special points. Well, we find this, and the generic transversal section is now the transversal Milnor fiber. It could look like this. The transversal singularity was A1, then here we will find the Milnor fiber of an A1 singularity in this hyperplane section. And we do the same thing as in the case of isolated singularities in the Turner transform. We look at the change of topology of all these local patches, and then we do Meyer-Vietoris to patch everything together to obtain a result about the global topology. First, let's consider this part away from the special point. We had a fiber bundle structure from Thom's first isotopy lemma and the choice of the stratification. And we had a fiber bundle structure here with fiber Y0 transverse, and here on the other side we have a fiber bundle with fiber Y transverse delta, the transversal Milnor fiber. And it's a fiber bundle over P1 without some points removed. It's a bouquet, a homotopy equivalent to a bouquet of 1 spheres. The whole topology is determined by the topology of this Y delta transverse and the monodromy actions around the special points. We know how to handle this. And then we also have the special points and the local Milnor fibers at the special points. It is what you see here in the green balls. And it's Milnor fibers of non-isolated singularities. And they connect to the blue part in what I call the second boundary. This Milnor fiber here in the green ball, it has a boundary, and this part of the boundary where it connects to the other patch is the second boundary. And to apply the Meyer-Virtores arguments, we need to determine the connectivity properties, or the relative homology groups with this second boundary. Of course, this part of the boundary has the same fiber bundle structure since it's a part of the blue part. And to tackle this connectivity, I had to use a theorem by Dirk-Siersma from 91. He doesn't state the theorem in this way because he didn't aim towards the application that I did with it. But I allowed myself to gather all the little pieces from his article and form one proposition that matches my needs, and it's this one. If you have a hypersurface line singularity, by line singularity I mean the singular locus is the germ of a smooth line. This is the setup that we have in the setup that we face here. Then we consider dimension greater or equal 3, and here the Milnor fiber and its second boundary, and then we can determine these relative homology groups. And basically what this says is that if we find any vanishing cycle here which is living below the middle degree, in this case for threefold degree 2, then it can already be found here in the second boundary. But the disadvantage of this theorem is that the way Dirk-Siersma did it was only for hypersurface line singularities, and here we have usually an arbitrary complete intersection line singularity. And therefore I try to generalize this theorem. I think I managed to. The result stays the same, only that we allow complete intersection. And the way we use it is the following. We have the local Milnor fiber from the special point up here, as I said. It has contributions in homology in degree 3 and 2, but everything in degree 2 lives already in the transversal Milnor fiber. Then we did not care about what happens at infinity yet. At infinity, I said, with a generic rank 1 perturbation, we still have y transverse infinity, which is this singularity, and we can use parallel transport in the fiber bundle to take any 2 cycle from here to infinity, and then we have a contractible space as a fiber, and that lets every 2 cycle collapse. So nothing survives in degree 2. We killed too much. Where does this generic cycle come from then finally? It comes from a section of this fiber bundle away from the special points, which also extends over the special points. You can prove this is the existence of this section with the result by Dirk-Siersma and the generalization by myself. And what we have then is the y delta of a rank 1, generic rank 1 perturbation, which might still have singularities here at infinity, but this is ISIS, and then you can smoothen that out and you're fine. Basically nothing bad happens when you smoothen this ISIS. And then you obtain this theorem. I was worrying that I should add smoothable EIDS, but it's apparent from the restrictions on the dimension. All right, this is, am I still on time?
Yes.
Yeah, then, yeah, where to go from here? I would like to discuss this in an updated version of the article by Terence Gaffney and Maria Ruas and Nivaldo Gurria. In the updated introduction, they speak of investigating how much the local Euler obstruction is functorial, in the sense that we pull back the Euler obstruction from here to here. And I think this question is related to what I want to do here. I want to understand how the cycles from here go over here. So this is something I would like to discuss, and once again like to invite you to our workshop in beginning of March 2018. If you're interested, please speak to me. Thank you very much for your attention. Congratulations, Federico, and yeah, I'll stop here.
Are there any questions?
In what extent your proof depends on the fact that you have an IDS, which is a form of dimensional singularity? It depends on this, or it depends only on the properties of the Turing transform that is local intersection?
The techniques here depend only on the properties of the Turing transform. We need local complete intersection and line singularity. If you take bigger matrix sizes, then you will have two-dimensional singular loci. You will have a threefold with two-dimensional singular locus, and then the stratification here will become much more difficult. And I don't know yet how to generalize these ideas from the theorem by Siersma beyond line singularities. This is the problem.
Two-dimensional determinantal singularity represented by 2 by 4 reaches, for instance.
Yes.
I think there are 2 points. One point is exactly this one that you said, the singular locus of the Turing transform, right?
Yes.
And but to go from the determinantal singularity to the Turing, you have also some properties that relate to the topology of the generic fiber of the IDS with the generic fiber of the Turing.
I'm not sure I understand. What do you mean by generic fiber?
In your paper we studied first, you relate to the topology of the superconjugate. The section is missing of the determinantal, correct?
Yes.
So with the generic fiber of the Turing transform.
Yes. If you have a smoothing, then they are isomorphic, because the underlying blow up is a blow up of a regular map. So yeah, of course this is a question, why should we be interested in y delta if we wanted x delta? Yeah, because y delta is isomorphic to x delta.
So once we have this and we can control the singular set of the Turing,
Yes.
the result can be your result holds.
Yes, yes. In the article I formulated for the Cohn-Macaulay codimension 2 singularities, since back then this was the only class of singularities where I could pin down the semi-universal unfolding and so on. They are still in the realm of the Hilbert-Birch theorem. But now with a more general setup of determinantal singularities, of course it makes sense to also consider other matrix sizes. And 2 by something matrices, they all work. This all works. But the problem is you can only grow the matrix in one direction. The other direction has to be limited.
You proved that the classification of early is given for could-dimension two Cohen-Macaulay singularities.
Yes.
All these simple could-dimension two Cohen-Macaulay singularities are determinable, or there are something else?
No. Cohen-Macaulay codimension 2 is this setup from the Hilbert-Birch theorem, and therefore they are all determinantal of certain type. Yes. Back then this was the original approach. And then what they classified was only the isolated ones. But there are also non-isolated Cohen-Macaulay codimension 2 singularities, and yes, all determinantal singularities are Cohen-Macaulay. Yeah.
More questions?